Hi, my name's Andrew McLaren, and I'm going to help you with a challenging problem. This is actually something I wouldn't expect to be on a college exam unless it's a more advanced college. Most of my students have the ones where one car's actually starting at being still, and the other one has to be moving at constant velocity, and eventually it catches up. If you have an initial velocity, this problem is doable. It's a bit harder to wrap your brain around, but I've given very simple numbers to help you see what's going on here. So the V average between these two things, we're trying to get to the point where that's the same. And that should allow us to see when these things have covered the same amount of distance, because V average is if we have the same value here, we have you know, something that we should be able to hold true where the time is the same, the V average is the same, and the distance traveled still has been the same. So this right here is like the big idea that holds this method together. These numbers, you can kind of see if one of them is traveling at 10 meters per second and the other one's starting at 5. This car is going to need to get the average of 10 meters per second. So the average that we're seeing right here is at 10 meters per second, which means if this is starting out at 5 meters per second, the other one is going to need to be an appropriate value that would get you up to 10 meters per second being the average. So you're saying like basically if this is at 5 meters per second and this is at or 10 meters per second right here, this final number should be appropriately high up, or like the difference between this is also the difference between that. So this should be at not 10, but 15 meters per second for its final speed. So you can see like the difference between its initial and final to the average is the same amount. So this should be having a final velocity of 15 meters per second. And when we do that, 15 plus 5 is 20. Divide that by 2, you get 10. Same as if you had 10 plus 10, then that should add up to 20 and divide by 2, give you the same average. So we're just basically saying at this rate of acceleration, when do we have a v final of 15 meters per second? And we know our acceleration is going to be the change in velocity over change in time. If we have that v final of 15 meters per second minus the initial of 5 meters per second, that is going to then be over time. And I've given you a very simple number, 1 meter per second squared for its acceleration here. If this was going at 2 meters per second, well, this would be taking less time to get up to 15 meters per second. So we've got 15 minus 5, so we've got a change of 10 meters per second all over this time at a rate of 1 meter per second squared. So it looks like this is taking 10 seconds for that to get going up to 15 meters per second. We know that that is going to be the amount of time that it takes for both of these things to go the same amount of distance. If we look here, our time was 10 seconds for both of them. Our V average for both of them is going to be 10 meters per second, meaning that the distance traveled is just 100 meters for our final answer for the distance traveled. And this is our time that we've traveled. Now, I gave you only 1 sig fig, so both these answers are going to be limited to 1 sig fig. But this is pretty straightforward math with the numbers that I gave you. But this would hold true as if I'd used like 20.54 and like 3.2 for these two values. Or if, like I can change any of the numbers here and the relationship still is true, but it's a bit trickier with the math. So that's the triangle method. You can also set these two equal to their formulas for position being equal to the v naught times time plus the acceleration times squared all over 2. That formula is going to hold true for both of these motions, but we have different values going in for them. So if we look at the method where we're doing a bit more of a comparison of these formulas, that is something that is still doable. It's just not how my brain wants to do this type of problem, like that triangle method, seeing that, well, it's not triangle now, it's what is that? I'm not going to even say it because I'm not sure. We've got a square and I think it's some sort of polygon. A rhombus? No, it's not. So if we look at this, now we have some values that we can start plugging in. Like we have a v initial for both of these objects. That's something that we do know. One of them does not have an acceleration value, so that's just 0 right there. So this whole thing is ignored. But we do have an acceleration value for the other one. So we have everything in here besides t. It does look a bit like a quadratic as of right now. We do know the distance at this point, but let's pretend that we don't. We're solving this a different method, right? So we have the v initial of the car that was going 5 meters per second. That's times some amount of time. And then it's going at an acceleration of 1 meter per second squared times this time squared all over 2. And that is equal to our other one, which was going 10 meters per second. Yeah. The whole time, its v initial is its v average times the time. And if we look at this whole expression, we can actually eliminate one set of time in the formula. If we divide everything by t, then we get something that's very similar, but simplified just a little bit to make the math actually doable. So let's get rid of one of our t's. And now you have everything in here in a nice expression that we can work with to solve for the amount of time. So we've got 5 meters per second, 10 meters per second. I'm actually going to suggest that we subtract the 5 meters per second here. And now we're left with 5 meters per second. And that's equal to this, what is that, 0.5 meters per second squared times t. And as you can see, time now has to be, what's that, 10 seconds. So you could find the time that way as well. And then you can just plug it into either of these two formulas. I'd probably plug it in here because it's an easier formula. So we can just take this relationship here and see that we've got 10 seconds. Which is the time that we'd said earlier. So I'm gonna actually mark that in green as our time, because that's the final time in our diagram here. And the velocity was, I believe, 10 meters per second. So our distance is 100 meters right there. You could also do it with your numbers that we had here for our blue motion, and that would also work out. In theory, it should give us the same number, because we now know that this is 10 seconds. For both of those times. And when we do that, it should work out. We've got, what is that, 50? I'm seeing 5 times 10, that would be 50 meters plus 10 squared would be 100 times 1, that's still 100, divided by 2, that's another 50. So yeah, it looks like this does go the same amount of distance here. We've kind of proven it with both of our position formulas. If you want a bit more of an in-depth explanation of either of those two methods. I do have different videos where I go over that, but like with an initial velocity of 0, this is just kind of like a capstone video showing the two methods a bit quicker, a bit more of a challenging problem. But there'll be a little playlist with the 3 of these in there, as well as all my physics videos. I've got in one other playlist as well.